All right, crew. So hopefully we've worked on that first part of the fundamental theorem of calculus, relating the derivative and the integral. Okay, how we could take the derivative of the integral to kind of what I would call cancel, to remove that integral and just have that interior function. But now let's look at the other side of that, the final part, the second part of our fundamental theorem of calculus. Okay. All right, so while this warms up, this is going to be the one part of our fundamental theorem of calculus that we're going to use predominantly in actually evaluating how we compute these definite integrals. Okay. And so, again, recall, think back that part one of our fundamental theorem of calculus was that when we're looking at a function, g of x equals that integral from a to x, pardon me, of f of t dt, that parameter, that dummy variable we call it, that kind of in place placeholder variable t, given that function defined to be that integral, then when we take the derivative, g prime of x, that's equal to f of x. Okay. So now, with that information, let's think back. What about our anti-derivatives? We talked about it in our textbook from section 4.9, right? Kind of going backward. We took a derivative, now going back, and hopefully with that in mind, that idea of having the derivative and integral being inverses, right? Kind of opposite operations, it's going to make sense to relate these, right? So remember, this capital F of x is the anti-derivative of f of x, right? Where when I took that derivative of capital F x, we got that function f of x. Right? So now, when I see that g prime is equal to f of x, then if I go to the anti-derivative capital F of x, doing that same operation of finding that antiderivative on both sides, that must be equal to g of x, right? So derivative of g gives me g prime. Derivative of capital F gives me little f of x. But that g of x, the way we define it up here, this is that integral from a to x of f of t dt. That's going to give me the capital F of x. Okay, so seeing that relationship between those components, is what's going to allow us to use the antiderivative with that integral. Okay, so with that said, that tool here, our second part of that fundamental theorem. All right, so part 2. The fundamental theorem of calculus. Okay, is that when we have this integral now, this definite integral from a to b, and we'll go to our f of x dx. Okay, so that integral, this definite integral, because we have a defined interval over which we're integrating. We have solid numerical limits of integration. That's going to be equal to f of b minus f of a, where here f of x is the antiderivative of that interior function, little f of x, that curve that we're finding the area below. We find its antiderivative, capital F of x, and we take the difference, always a subtraction, the upper limit, take away lower limit. Okay, it's always a subtraction. And so some notations here. When we work on these, this integral from a to b of that function f of x dx is equal to, okay, one way we start to see it, in full brackets here, capital F of x in the brackets, our antiderivative, and then our limits of integration slide to the other side. So our work becomes looking for the antiderivative, and then instead of the integral symbol, the dx falls away. We take those limits and put on the outside of those brackets. And that's equivalent to just on one side a bracket, or a vertical line. Okay. Right, as mathematicians, we were talking about kind of we're lazy with our notation. We want to write as little as possible to mean as much as possible. But again, all this tells us to do our antiderivative with the upper limit minus the antiderivative evaluated at the lower limit, always a subtraction. And that's how we're going to compute. And we should do this and we get a real number result. Okay, you can compute to get a real number result. So typically at this stage for a definite integral, there's no variables left. We're plugging in and computing. And we might get an exact value. You might have like a pi and e to the second power. I'm not going to compute the long decimal, but a real number that if I wanted to punch into a calculator, I can get, but no variables. And as we see, the real work is looking for that antiderivative. Okay. All right. So let's look at some examples here. Computing, evaluating, using this second part of the fundamental theorem of calculus. And this is when remembering some of those antiderivatives, remembering our derivative rules is going to come into play. Okay. So with these problems, let's evaluate this integral, or I'll say even more precisely, this definite integral, but it has these limits of integration. And let's just borrow the problem number 22 on page 400, the integral from 0 to 1 of 1 minus 8, and they use the variable v cubed plus 16 b to the 7th dv, right? That variable should match our variable of integration. So when I go to evaluate that integral, my f of v, sorry, not f of x, 1 minus 8v cubed plus 16v to the 7th, we need to find our anti-derivative. And going back to our discussion of looking for the antiderivative of functions, of terms, kind of like our reverse power rule, when we start to go through that one, we're going to get the variable attached. That coefficient stays, and then we get our variable. Because if we take the derivative of that v to the first, it's just 1. V goes away. We're right back where we started. Now, we're going to have here minus 8. And now that v to the third power, remember, we add 1 to the exponent, divide by the new power. That's that power rule for the antiderivatives. Plus 16, same idea. V to the 7 becomes v to the 8 over 8. So there's my antiderivative. And we're going to take those limits of integration and compute. So our this kind of step-by-step process. And again, if we need to off the side work on building up those antiderivatives, most definitely we can do so. But now as we start to compute, plugging in, substituting in, or here, let me actually simplify here. That's just v, 8 over 4 makes 2, v to the 4th, 16 over 8 becomes 2, v to the 8, there we go. A little better simplifying. But now we're going to plug in first our upper limit of integration. Put my placeholders in. V is 1, 2 times 1 to the 4th plus 2 times 1 to the 8th minus, it's always a subtraction. And now for my lower limit of integration, and again, bringing in my placeholders. 0 minus 2 times 0 to the 4th plus 2 times 0 to the 8th. All right, well, this side over here, that's just 0, of course. That's going to go away. Computing within that first bracket, my upper limit, 1 to the 4th is 1 times a negative 2 minus 2. 1 to the 8th is 1 times positive 2. And we start to go through right here. So we're going to take negative 2, positive 2 go away, 0 goes away. So all that's left in the end is 1. Right? And so what this represents for us, so this is our area under, or that net area under that curve, 1 minus 8v cubed plus 16v to the 7th over the interval from 0 to 1. So if we were to graph that and look how much space is trapped between the x-axis and that function, it's going to be exactly equal to 1. Okay. Let's check out another. Check out problem number 34. Okay, this integral from my numbers here, 0 to 3 of this function, 2 sine of x minus e to the x dx. Right? So in this case, our function that we're integrating, that we're going to be finding that antiderivative for, two sine x minus e to x, right? And so this is where we have to think back, right? Remember, think back, remember that when I take the derivative, of cosine, that's giving me negative sine of x. The derivative of e to the x is that same e to the x, right? So when we start to look at this integral, this definite integral, thinking about that antiderivative, the 2 is going to stick around. To get that positive sign, I need to take a derivative of a negative cosine x, right? Derivative of just cosine's negative sine. If I want it to be positive, I bring an extra negative. Derivative of a negative cosine is going to give me negative of a negative sine, or positive sine there. The minus 6, the derivative of e to the x, or antiderivative of e to the x, right? Well, derivative of e to the x gives me e to the x again, so it's the same antiderivative, like so. Bring in our limits of integration from 3 to 0. Doing a little bit of cleanup. Negative 2 cosine x minus e to the x from 3 to 0. And now computing, plugging in that upper limit of integration. Negative 2 times the cosine of 3 minus e cubed. And again, I'm not sure what those values are precisely, but I can put a decimal in if I wanted a calculator, or I'll just leave it in this exact form, as I'll call it. Minus 2 cosine of 0 minus e to the 0 power. And just real briefly, cosine of 0, that's positive 1. E to the 0, positive 1. So when I go to compute, negative 2 cosine of 3, that's some decimal I'm not sure of, minus e cubed, another decimal I don't know. But here we go, negative of a negative makes that a plus. 2 times 1, so positive 2. Negative negative is positive. 2 times 1, 2. Negative negative plus e of 0 is 1. So sneaking down here, negative 2 cosine of 3 minus e cubed plus 3. And again, if I want to punch in the information to a calculator, remember, that's in radians, not degrees, we can evaluate. But leaving it in that exact form, perfectly fine. All right. So this fundamental theorem of calculus, second part, when we evaluate these definite integrals, you find your antiderivative, keep track of your limits of integration, and we take the difference. Upper limit, take away lower limit, evaluate, simplify, combine like terms as much as possible. But in our final answer with a definite integral, no variables remaining. Okay? All right.